The research optimizes the expected volume of a sumset formed by combining set A with n random points from set B in ROAD. The authors aim to minimize this volume by determining the optimal choice of A and B. They proved that Euclidean balls should be chosen for A and B to achieve this minimization. The study also extends to the torus TD, where the optimal choice is shown to be bands. The results include a theorem and its corollary, providing estimates on the number of random points needed to ensure the expected volume is close to the true lower bound given by the Brun-Minkowski inequality. In the torus TD, the authors tackle the problem of minimizing the expected volume of the sum of a set A and n points chosen uniformly at random from a set B. Theorem 1.3 establishes that for A and B with identical volumes as bands A and B, in TD, the expected volume of the sum of A and n points from B is at least the expected volume of the sum of A and n points from B. This theorem enables the estimation of the number of points needed to ensure that the sum of A and n points from B has a volume of at least min A plus B 1 epsilon on average. A corollary 1.4 provides explicit lower bounds for the expected volume of the sum of A and n points from B in terms of the volumes of A and B to prove their main result in Euclidean space. Theorem 1.1. The authors adopt a novel approach. They first establish a discrete version of the result in one dimension in the group ZP. Theorem 1.5, which states that for sets A1 and in B1, Bn of the same sizes in ZP, it is optimal to take the sets to be intervals centered at 0 or 1/2, depending on parity. The use of the cyclic group ZP is crucial, as it allows for transforming unions into intersections, essential for their proof. The authors then extend the discrete result to the continuous case in the torus and Euclidean space using symmetrization and discrete approximation. Although the torus is not isotropic, they demonstrate that sufficient symmetrizations are possible to solve the problem in 2 dimensions, and subsequently, in the general case. Additionally, the authors examine stability versions of their results, which investigate how close the sets A and B must be to the lower bound. These findings provide novel insights into the problem of minimizing the expected volume of the sum of a set in randomly chosen points in the torus and Euclidean space. The paper explores extremal sets for an inequality, focusing on stability results for 2 main theorems. It proves sharp stability versions of these theorems without relying on the actual inequalities, providing alternative proofs. The paper's structure is outlined, covering the main tool, its translation to a continuous setting, and the proofs of the theorems. It also includes calculations and stability results. The notation and conventions used are explained, emphasizing the significance of certain measures and intervals. The proof of Theorem 1.5 is detailed, focusing on the case where P is an odd prime. This involves an inequality involving characteristic functions and convolution, crucial for the stability results. For any 1 is less than or equal to I is less than or equal to n, claim 2.1 asserts 2 inequalities. The first inequality, part A, states that the summation of max 0 bddibd by x j over x in ZP is less than or equal to the summation of max 0 bddibdb x j over x in ZP, where x0, x1, xp1 is a specific sequence. The second inequality, part B, states that the sequence bddibdb xt is decreasing. This claim relies on Theorem 2 in reference 7, establishing a relationship between the summation of min bddibd by x j and the summation of min bddibdb x j. By noting d equals di and by equals b, the authors derive an equivalent inequality involving the summation of max 0 bddibd by x j and the summation of max 0 bddibdb x j. This inequality is then proven by rearranging the terms. Claim 2.2 consists of 2 parts. The first part states that the summation of the product of bddibd by x over I and x in ZP is less than or equal to the summation of the product of phi x over I and x in ZP, where phi is an increasing function with the same profile as bddibd by. The second part asserts that the summation of the product of bddibdb x over I and x in ZP is equal to the summation of the product of gi x over I in X in ZP, where Gi is an increasing function with the same profile as BD/BDB. The proof of claim 2.2 relies on the rearrangement inequality for the first part and a functional equality between Gi, X, and BD/BDB, sigma, X, where sigma is a permutation on ZP. This functional equality is established by showing that Gi and BD/BDB composed with sigma have the same profile and are increasing functions. The research paper discusses a series of lemmas and theorems focusing on the properties of increasing functions and their applications in number theory. Specifically, lemma 2.3 establishes a relationship between two increasing functions phi and Gi over the integers modulo p, stating that the product of phi, x, across all integers is bounded above by the product of Gi, x, under certain conditions. The proof involves a series of logical deductions, starting with the claim that for any I and any r in ZP, the sum of phi, x, over all x equals the sum of Gi, x, over all x. This leads to the main result, which is then used to prove theorem 1.5. The passage also touches on the continuous case, mentioning a lemma that deals with measurable subsets and their properties in the context of random sampling. The authors introduce a probabilistic construction to analyze the difference in expectations of two quantities. They define random variables y and y uniformly distributed in y and y, respectively, and consider the event y where y equals y for all I in n. The probability of the complementary event e(c) is bounded by the sum of y intersection y, max, y over I in n. Conditioned on e, they establish an inequality relating the difference in union sizes of xi plus y and z plus y to the sum of xi hollow-up pointing triangle z over I in n. Combining this with the probability estimate, they derive an upper bound on the expectation of the difference in union sizes. The authors then present corollary 3.2, which states that for sets A1, and in B1, Bn of positive measure in the torus T, and their corresponding intervals A, 1, on and B, 1, Bn, the expectation of the union size of I plus bi is at least the expectation of the union size of I plus b, where bi and b are chosen independently and uniformly at random from bi and b, respectively. The proof of corollary 3.2 involves approximating the sets I, bi, I, and b with discretized versions C, D, Ki, and Di, and applying the previously established inequality. The authors also introduce claim 3.3, which provides a similar inequality for the discretized sets, with an additional error term depending on the approximation error epsilon. The proof constructs subsets of ZP, denoted as xi and yi, and their discrete interval counterparts, z and yi, centered around 1/2. The cardinalities of xi and z are equal, as are those of yi and yi. The variables yi and yi are defined as the ceiling of PDI and PDE, respectively. When d and di are chosen uniformly at random from d and di, respectively, then yi and yi are also chosen uniformly at random from yi and yi, respectively. The inequalities, union text I, c plus d, minus 1p, union text I, xi plus yi, is less than or equal to knp and, union text I, c, I plus d, I, minus 1p, union text I, x, I plus y, I, is less than or equal to knp are derived, which are then combined with theorem 1.5 to conclude that e, union text I, c plus d, is greater than or equal to e, union text I, c, I plus d, I, minus 2 knp is greater than or equal to e, union text I, c, I plus d, I, minus 2n epsilon. By applying lemma 3.1 and the fact that C hollow-up pointing triangle I is less than or equal to epsilon I, D hollow-up pointing triangle bi is less than or equal to epsilon bi, C, I hollow-up pointing triangle A, I, is less than or equal to epsilon A, I, and D, I hollow-up pointing triangle B, I, is less than or equal to epsilon B, I, it is shown that E, union text I, C plus D, minus E, union text I plus bi, is less than or equal to 4n epsilon, summation display I, is less than or equal to 4n2 epsilon, and similarly for the primed variables. These inequalities are then combined with claim 3.3 to obtain E, union text I plus bi, is greater than or equal to E, union text I plus B, I, minus 2n epsilon minus 8n2 epsilon. As epsilon can be chosen arbitrarily small, it is concluded that E, union text I plus B, is greater than or equal to E, union text I plus B, I. The concept of Steiner symmetrization of a measurable set X in Td is then introduced, denoted as SD, X, which is a measurable subset of Td that has the property that for every U element of Td-1, SD, X, U is a closed interval in T centered around the origin with SD, X, U, equals, SHU. The Steiner symmetrization is generalized to an integer D times D matrix M with det, M, equals 1, denoted as Sm, which transforms a measurable set X in Td into the set Xm equals Sm, X, in Td. It is noted that M induces a measure preserving bijection Td right pointing arrow Td. Finally, lemma 4.1 is stated, which asserts that for every M element of SLD, Z, and for any measurable subsets X and Y of Td, we have Xm hollow up pointing triangle Ym is less than or equal to X hollow up pointing triangle Y. The proof of the main result leverages the fact that the determinant of M is 1, reducing the problem to the case where M is the identity. This enables a focus on the unidimensional case, where the goal is to show that the symmetric difference of the Steiner symmetrization of two sets X and Y is bounded by the symmetric difference of X and Y. A crucial step in the proof is the establishment of lemma 4.2, which states that for any measurable set X in T squared, there exists a sequence of matrices Mj in SL, Z, such that the sets Xj, defined recursively as Xj plus 1 equals Mj, Xj, converge to a band X, with the same area as X. This convergence is uniform in X. The proof of lemma 4.2 relies on the construction of the matrices Mj, which act independently in each section T times U. The matrices are designed such that Mj, X, equals X, for all J, ensuring that the symmetric difference, Xj hollow up pointing triangle X, decreases as J increases. The remainder of the proof involves a detailed analysis of the sets Xj and X, focusing on the case where X2J plus 1 hollow up pointing triangle X, greater than 4 epsilon. This leads to the definition of the sets S and B, which are used to establish claim 4.3. This claim states that for every J is greater than or equal to 2, epsilon and T element of T, the intersection of the sets I, T and I is bounded below by the intersection of the sets IT and I, plus an additional term involving J and epsilon. The proof of claim 4.3 relies on the bijective functions f and g, which are used to establish the lower bounds on the measures of the sets S and B. These bounds, in turn, are used to show that S is disjoint from it and B is contained in it, completing the proof of claim 4.3. The proof of claim 4.3 establishes that for every J greater than or equal to 2, epsilon, either the difference between X2J plus 1 hollow up pointing triangle X is less than or equal to 4 epsilon or the intersection X2J plus 2 intersection X is greater than or equal to X2J plus 1 intersection X plus J minus 1 epsilon. This is achieved by showing the empty intersection of S with it, leading to the conclusion that B is a subset of it. This completes the proof of claim 4.3. The discussion also explores corollary 4.4, which demonstrates the existence of matrices Mj in SLD, Z, that ensure the difference between Xj and X decreases uniformly as J increases, achieved through a series of symmetrizations. Finally, lemma 4.5 compares the expected measures of sets before and after Steiner symmetrization. The proof of the theorem begins by assuming, without loss of generality, that the identity M is the same distribution as Y, U, for all U element of Td-1. This allows for the coupling of Y and Ym so that equals UI and, conditioned on UI, Z and Zm are independent and uniform. The proof then proceeds to show that E, union text I, Xi plus Y, is greater than or equal to E, union text I, Xmi plus Ymi, by conditioning on U, U1, an element of T and choosing Z and Zm uniformly at random. This establishes a connection between the original and symmetrized variables. The theorem's proof concludes by using corollary 3.2 and lemma 4.5 to demonstrate the inequality. Another approach to proving the theorem is also discussed, starting from a discrete setting result. The authors discuss alternative approaches to deriving theorem 1.3, including using Dow's result and Pollard-type inequalities. They then focus on the derivation of theorem 1.1, introducing Steiner symmetrization. For a subset X of Rho and U in Rho 1, Shu is defined as X, U, in X. The Steiner symmetrization SD, X, of a measurable subset X of Rho is defined as a closed interval in R centered around the origin, such that SD, X, U, equals Shu. A more general Steiner symmetrization SM is introduced, transforming a measurable set X in Rho into XM equals SM, X, in Rho. Lemma 5.1 states that for points y1, yn chosen independently and uniformly at random from Y, and ym1, ymn chosen independently and uniformly at random from ym, we have E, union I, x plus Y, is greater than or equal to E, union I, xm plus ymi. The proof involves assuming without loss of generality that M is the identity, scaling x and y by a sufficiently small parameter alpha greater than 0, and applying the canonical map pi 1/4, d right pointing arrow td to reduce the problem to lemma 4.5 for sets pi, x, and pi, y. The proof of theorem 1.1 is then presented, involving a sequence of Steiner symmetrizations to measurable sets A and B, producing AC and BK for K in N, and showing that E, union I, AC plus BKI, is greater than or equal to E, union I, AC plus 1 plus BK plus 1I, for K in N. The theorem is generalized to theorem 5.2, stating that for measurable sets A1, N, B1, Bn in Rho of finite positive measure, and for bi, B chosen independently and uniformly at random from bi, B respectively, we have E, union I plus bi, is greater than or equal to E, union I plus B. Estimates are provided to prove corollary 1.4 and corollary 1.2, showing that for A and B as intervals, the points B1, Bn can be ordered such that bi1 has the same distribution as B1. The distribution of the minimum of Ni, I, D, random variables uniform on 0, B, is discussed, establishing that the distribution of B1 is the minimum of Ni, I, D. Random variables uniform on 0, B. The distribution of bi minus 1 is shown to be the same as B1 minus 0 equals B1, conditioned on B for any choice of bi. This unconditional distribution is used to calculate the expected length of the union of intervals A plus bi for I greater than 1. The calculation involves the probability that the smallest of n plus 1 uniform numbers in 0, B, is at most A, which is 1 if A is greater than or equal to B and 1 minus A, B, n plus 1 if A less than B. This result is used to prove corollary 1.2, discussing the expected volume not covered by the union of intervals A plus bi. The proof involves a detailed analysis of the region close to the boundary of the ball A plus B, showing that the expected volume not covered is proportional to epsilon, d plus 1, 2, where epsilon tends to 0. The expected fraction of A plus B not covered by the union of A and B is derived using the constant Ca, B, d involving an integral. This expression is dominated by the range when epsilon is very small, allowing for an approximation by an exponential. The expected fraction is then shown to be 1 plus 1, dA plus B for some constant C, depending on A, B, and D. This constant C remains unchanged by uniform scaling of A and B. The section also discusses the sharp stability result for theorem 1.3, which involves proving a stability result for Bohr sets in TD. The theorem states that for epsilon greater than 0 in D, n element of n, there exists K such that if A and B are measurable subsets with epsilon is less than or equal to A, B, is less than or equal to 1 minus epsilon, and A and B are intervals centered around 0 with the same measures, then there exist parallel Bohr sets X and Y such that A hollow up pointing triangle X, B hollow up pointing triangle Y, is less than or equal to K delta 1/2. The exponent 1/2 is optimal, as shown by an example. The section concludes by stating some inequalities of Riesz-Sobolev type and their stability versions, which are used in the proof of Theorem 7.1. The development of Theorem 7.4 is a key component in the analysis, establishing a connection between the measures of sets and the behavior of certain functions. It states that for given compact sets A and B in a space Td, there exists a relationship between the integrals of functions over these sets and their transformed versions. This is derived from a more general result, Theorem 7.5, about arbitrary functions. The proof involves the application of integration by parts and the properties of decreasing functions, with significant implications for the understanding of set measures and their interactions with functions. Theorem 7.4's proof revolves around the decreasing rearrangement of continuous functions. This concept is introduced, along with its unique properties, which are essential for the theorem's core argument. The core argument demonstrates the equivalence of integrals over specific sets for the original and rearranged functions. This is accomplished through a series of inequalities, leveraging theorems 7.2 and 7.5. The proof's culmination lies in establishing that the integral of the original function over a set is bounded by the integral of its decreasing rearrangement over the same set. Crucially, these bounds converge as the set size decreases. This theorem is pivotal in understanding the properties of decreasing rearrangements and their applications in functional analysis. The decreasing rearrangement of a continuous function is uniquely characterized by its monotonicity and equimeasurability properties. These properties enable the establishment of inequalities which, in turn, facilitate the equivalence of integrals. The application of theorems 7.2 and 7.5 is instrumental in bridging the gap between the original and rearranged functions. Ultimately, the theorem's significance lies in its far-reaching implications for functional analysis, where the properties of decreasing rearrangements play a vital role. The theorem's conclusion, namely, the boundedness of the original function's integral by its decreasing rearrangement's integral, has profound consequences for the field. The authors derive an inequality by taking the complement of the sets inside Td and T, yielding the expectation of the intersection of AC plus B and AC plus B being greater than or equal to delta plus the expectation of the intersection of AC plus B. After scaling and applying bounds on B and B, the inequality is rewritten as an integral display, which is further simplified by setting D equals AC and D equals AC plus 1/2. The authors then apply theorem 7.4 with parameters epsilon, 2, n, and alpha equals tau delta, 1 epsilon, to the power of n to the sets D and B, establishing the existence of a compact set C and Td with specific properties. By theorem 7.3 with parameter epsilon, 2, parallel Bohr sets W, Y, and Z in Td are obtained, such that the symmetric difference between D, B, and C with W, Y, and Z, respectively, is bounded by k delta squared. A sharp stability result for theorem 1.1 is then introduced, stating that for epsilon greater than 0 in D, n element of n, there exists k equals k, epsilon, D, n, greater than 0 such that for measurable sets A and B in Rho, if the expectation of the sum of A and a random subset of B is less than or equal to delta plus the expectation of the sum of A and a random subset of B, then there exist homothetic ellipsoids X and Y in Rho such that the symmetric difference between A and X, and B and Y, respectively, is bounded by k delta squared. Notably, the exponent 1/2 in theorem 8.1 is optimal, and the proof relies on the Riesz-Sobolev inequality and its stability version. Theorems 8.2, 8.3, 8.4, and 8.5 form the foundation of this research, providing critical insights into the relationships between measurable subsets, compact subsets, and their corresponding geometric representations. Theorem 8.2 establishes a precise connection between measurable subsets and their associated balls, setting the stage for subsequent results. Theorem 8.3 introduces the concept of compact subsets and their homothetic ellipsoids, which play a vital role in understanding the geometric structure of these sets. Building upon this, Theorem 8.4 ensures the existence of homothetic ellipsoids for compact sets subject to specific volume constraints, further solidifying the connection between sets and their volumes. Theorem 8.5, a cornerstone of this research, relates the integral of a function over a set to its homothetic version, providing a powerful tool for analyzing and comparing functions defined on different domains. Theorem 8.6, a general result applicable to arbitrary functions, serves as a crucial stepping stone in deriving the main result, underscoring the importance of these theorems in establishing connections between sets and their volumes. The authors apply the function h, x, equals 1g, x, caret, n1, plus 1g, x, caret, n2, 1f, x, plus 1f, x, caret, n1, leveraging the properties of g, x, and f, x, to deduce that the integral of 1g, x, caret n dx is less than or equal to the integral of 1f, x, caret n dx. This is further bounded by gamma I, caret, n1, beta. In the proof of Theorem 8.4, the authors consider a continuous function h. Rho right pointing arrow, 0, 1, with bounded support and its decreasing rearrangement h. 0, infinity. Right pointing arrow, 0, 1. They define f and g as the decreasing rearrangements of BDA asterisk operator, BDB, B, and BDA asterisk operator, BDB, B, respectively. Notably, BDA asterisk operator, BDB, B, rho right pointing arrow, 0, 1, is spherically symmetrical and has a decreasing property, allowing the definition of g, x, as a function of Vd, x, caret d. The function g, x, has a continuous negative derivative for rho d less than x less than rho d plus, where rho and rho plus are defined accordingly. Setting I equals rho plus epsilon, and j equals rho plus epsilon, d, the authors establish that there exists a gamma greater than 0 depending on d and epsilon such that for x element of j, g, x, is less than or equal to gamma. They then define C, T as the ball centered at the origin in rho with volume T and utilize the properties of BDA, asterisk operator, BDB, x, and f, x, to establish an integral inequality. Finally, the authors use the definition of decreasing rearrangement to show that the integral of f, x, dx is equal to the integral of g, x, dx, and apply Theorem 8.2 to deduce an integral inequality involving f, x, and g, x. The proof of Theorem 8.1 is established through the application of Theorems 8.3 and 8.4. Specifically, constants c and tau are derived from these theorems, and k is set as c tau minus 1/2. To approximate measurable sets with compact sets, we assume A and B are compact in rho. The proof involves a series of inequalities that leverage the properties of decreasing rearrangements and the hypotheses to demonstrate the theorem's conclusion. A crucial step is to show that the integral of a specific function over a set C in rho, bounded by certain parameters, is greater than or equal to a value minus the integral of another function over a centered ball in rho, also bounded by specific parameters. This process relies heavily on the mathematical concepts and theorems presented earlier in the paper, connecting them to derive the theorem's conclusion. The proof's success hinges on the careful application of these mathematical tools, which enable us to establish the theorem's conclusion. By combining theorems and inequalities, we can demonstrate the desired result, providing a rigorous proof of Theorem 8.1. The authors of this research paper pose several open problems that arise from their investigation. One such problem involves selecting points uniformly at random from the boundary of a set B, rather than the entire set, and examining the resulting sumset. This problem can be quantified in two natural ways. Either by choosing from the set of points at a distance of at most epsilon from B, or from the set of points between the 1 plus epsilon dilated and epsilon eroded versions of B. These approaches exhibit different biases towards the shape and curvature of the boundary. Another direction for future research is to consider the convex hull of n random points in sets A and B in rho, and investigate whether Euclidean balls still minimize the expected value of this quantity. The authors propose a variation of their results, where instead of using random points, they use random copies of a fixed body, such as unit intervals with random centers and orientations. Furthermore, they suggest allowing the extra body to vary by being related to B, for instance, by being a homothetic copy of B. This leads to questions about minimizing the expected volume of the sumset of A with n random copies of B, 2, chosen uniformly at random from the copies of B, 2 inside B.